it'll take me a little while to warm up to this because I haven't done it for a long time. But so the publication, you ready? The publication was the Tesla and Alexanderson system of radio. So I'm going to work on that, and then I got to work my way out so that you know what radio is. And did you bring my book, George?
It's right here.
A big one with all the pictures in it.
I did not bring that one.
Uh-oh. That has all the pictures.
Needed that.
Okay, well, we'll do without them.
We can send Catherine back for it, and she can bring it back within an hour. Would that work?
No, I'll just adapt. Because at any rate, you opened up at the right places. I have to figure out some way within about 45 minutes so that everybody can understand what that page means. So how many people here know what a quadratic equation is? Oh, that's pretty good. How many people know what a differential equation is? Oh, okay. Well, that's good. How many people know what Heaviside's telegraph equation is? Oh. How many people perform or play music? Okay. How many people wrench on engines, motors, pumps, circuit breaker boxes? Okay. So it looks like everybody will kind of, I can make an analogy. So the thing is this being the Tesla Society and all that, nobody ever seems to talk about who Tesla is. How many people here know who Tesla is? Okay. How many people know why his name stands out from everybody else? Okay, so Tesla is not a complete unknown. How many people get upset when you say Einstein's theory of relativity is wrong? There, good. Okay. So what you will get is the first public presentation of the theory of anti-relativity. Okay, so Nikola Tesla was a pinnacle in the electrical engineering world, which basically doesn't exist anymore. There's no electrical research anymore. There's no electrical laboratories. No one's ever bothered to complete the unfinished equations or all the mistakes or the whole situation. So we got to kind of go all the way back in order to understand what Tesla and his contemporaries are working on. Now, you have to keep in mind with regard to Nikola Tesla, he wasn't just like a soul flash out of the blue individual that appeared from nowhere and just figured all this stuff out. What Nikola Tesla did is he rode the wave of an intellectual movement at the time. He was the peak of it, the quintessence of all the studies and theorizing and the math and everything that had accomplished with the start of a person by the name of Galvani would really be your beginning in all this. An Italian medical man that found that certain pieces of metal would cause animals' legs, if they weren't too deteriorated on the dissection table, to jump and twist. And then Galvani found that when there was a lightning storm, the legs would flop around on the table without any metal. So Galvani invented the antenna to experiment with what there was in space that made the animal's legs jump, and the detector that Galvani had at the time was the muscle tissue response to electricity. It didn't have any diodes or vacuum tubes or relays or magnets or nothing. It was just simply his detector was a biological organism that still responded to electrical stimulus. So what Galvani found was that there's an atmosphere around all metals. This atmosphere is different for each metal. It's identified with that metal. So if you have a metal of zinc and you have a metal of copper and you have two sheets of it and you have them all shiny, is in between them is an electrical condition. And this is what I'm going to have to explain to everybody so they can understand is what is in between this space. Okay, now later what happened is a guy by the name of Volta found that if he took this electrical atmosphere situation, okay, and it involved what's called an electrolyte, which is a fluid like salt water or lemon juice or something either strongly acidic or alkali, something basically corrosive. And you put this metal into a sandwich with the liquid in the form of a gauze or paper or jelly or something to hold it. Now all of a sudden this electrical influence can be conveyed from one metal plate to the other and produce fire. By putting a piece of metal across, you start to get fire. So what Volta did is he started compounding these little what are called cells and getting a higher and higher and higher amount of this electrical condition until eventually he could produce a standing electrical flame. Now this was the first time that mankind has ever been able to produce a continuous electrical discharge condition, because previous to that it was either permanent magnets, which you can't really get any electricity out of, and electrostatics, which you can't really get any electricity out of. And the reason is you can't have electricity until you have its two components, which is either electrostatic or magnetic. Now, when the chemical cell was developed by Volta, now was the condition where not only did the atmosphere of the metal create the electrostatic condition, but the current flow through the metal of the chemicals trying to readjust through the dielectric or the electric medium, electrolyte, and the metals produces a current flow. Okay, of course, none of these people knew what any of that was back then. So a man by the name of Michael Faraday made an extremely important discovery that basically initiated the entire electrical age, and very little has changed since Faraday. Faraday found that in experimenting with this voltaic battery, as it's called, the word battery means like a line or a compounding of things. So a battery is a number of cells, a battery of cells. So if you have the thing that you put in your flashlight or your radio or whatever is not a battery, it's normally a cell, and then you use a number of them to make up a battery. So Faraday experimented with the battery and the wires and making the sparks, studying the sparks, and then what he found is the compass on the table, pointer would move every time he was drawing the sparks. And what Faraday found is that magnetism was appearing even though there was no magnets. And that was the beginning of what we call electromagnetism, which is the basic foundation of all of our technology, to the point where it's become almost like a religion. It's a social mind virus, so to speak, or an icon, archetype. And everything is based on this electromagnetic mind reality. So what Faraday theorized was, if the compass is sitting on one place on the table and the inductive device that produces the magnetism is on the other end of the table, what is there in between? And this is where the understanding of electricity evolved from. So Faraday experimented, and he found, now how many people here have ever been like in a school classroom where they take the iron filings and they put them on a piece of paper and you put the magnet underneath? Okay, good. Most people have seen that. Well, the iron filings form little fibers. You notice they tend to bind together into a fibrous structure. So what Faraday concluded is that there was a fibrous structure in space that was responsible for action at a distance. Now, at the same time, you had Isaac Newton, who was claiming gravity worked through nothing. There was no intermediary field, and came up with the concept of action at a distance. In other words, action at a distance means you can affect an object at a distant point without anything being in between. Well, there's something nonsensical about that. What's that?
If you believe in God, you can have a science like that.
Well, okay, I suppose. But at any rate, it didn't go that way. So the conflict broke out between whether there was something in between or not in between. So Faraday came up with the idea of what's called the ether. The ether is a spatial medium, what Tesla referred to as an ultra-rarefied gas. And actually, when Mendeleev worked out the periodic table of elements, he postulated through the use of the periodic table of elements it was possible to predict elements that were not yet discovered because of the harmonic sequence of all the elements. And this led to what we would call the pre-hydrogen elements. So it seems to be there's some kind of primordial atmosphere that permeates everything, and that's what Faraday theorized it existed. And it's referred to as the primordial ether. And the ether, when it becomes polarized through some type of hydrodynamical process, like twisters and tornadoes and vortexes of water going down holes and what have you, that these lines of force were appearing in this ether. If there was a a motive force or something to cause this to want to exist. It's a condition of imbalance in a normally static ether. So it didn't go too far with that idea until telegraph guys picked up on the fact that what Faraday had also found was if you take this wire that you drew the fire with, and the compass points towards it, well, if I take that wire and I compound it on itself once, twice, 3 times, 4 times, each of the current flows passing over and over give the effect of a higher current. So if I have a current of 1 unit flowing through a wire, if I take that wire and coil it around so that every part, the wires are going in the same direction, it'll be 1 amp, 2 amp, 3 amp, and if I put 100 turns of wire on there, I have 100 amps. Now I have a magnetic field that makes iron jump around on the table, not just compasses. And this was the beginning of the electric motor and the telegraph relay. The telegraph relay kind of had a weird start in all this because it was developed by a painter by the name of Morse, who knew nothing about electricity, but enough experiments had been done that it was now known that electricity could be conveyed with a transmission structure from point A to point B. A monk in, I think it was France, did the final experiment of connecting the entire town's folks together, hand to hand with 25-foot pieces of wire in between, and discharged a giant electrostatic condenser, which at that time had just been developed by Franklin. And everybody jumped simultaneously. They made a line 1 mile, and everybody jumped together. And at that point, that was the final proof that electricity was then thought instantaneous and can be conveyed to any point. So people worked with it and fooled around, and then Morse came up with the initiative that he was going to push it forward and do it. So what he did is enlist the help of Joseph Henry, which was basically duplicating Faraday's experiments here in America. He's also responsible for starting the Smithsonian Institute and a number of other things. He's kind of a forgotten American scientist. And they worked together and came up with the relay coil that would pull the sounder or the key or whatever it was that you were trying to signal from point A to point B. And then they worked out the wire process. So it turned out to be you have to have in electricity what's called a boundary condition, where the wires enclose completely the electrical situation, and then once you have that, which is called a circuit, then you can get the batteries and the electromagnetic thing to work in a circuit. Now, a guy in Germany by the name of Steinhill decided that, well, let's see if we can use the Earth as the other boundary. In other words, the grounded telegraph line. Of course, all the experts immediately said the Earth is so giant it will just absorb up all the electricity and it'll never work. I mean, after all, that makes absolute sense. But Steinhill did it anyway. So he put the whole thing together, and lo and behold, it worked just fine. And not only did it work just fine, but a lot of stations didn't need batteries anymore. So instead of the electricity disappearing, the electricity was appearing. Then the question had to be, well, where was this electricity coming from? So being that the Earth was being used as part of the transmission structure, the Earth inside is a massive reservoir of electricity, and it's in constant motion, usually in some type of impulse form of waves ringing and echoing and bouncing, and there are literal seas of electrical current, rivers of it, flowing from one point to the other, and that's what gives the Earth its magnetic field. It's this incredible current flow. So that started to do more and more of these problem things started to work their way into the telegraph situation. So it started to be that in the telegraph offices, on certain days, the telegraph sounders would just be clacking away on their own, like the ghosts were operating them. And what it turned out to be, what the problem was, is the Earth was being impacted by solar flares, and it took basically the telegraph business to determine a lot of things now that, is considered general scientific facts. It was the telegraph that forced most of these things to be analyzed and discovered, was the problems. So then they started to get a better idea of inductivity and antenna type considerations. And so they had to use like pairs of wires, and they had to go back to the original closed circuit during magnetic storms, which cut the number of wires in half, but that was the only way around it. And there's a lot of scientific study done during that period to determine what are called telluric currents. This is what my whole earthquake system is based on. Is this interference becomes the signal rather than the noise. But I'm not going to get into that. This is a specialized deal. I'm trying to cover the Tesla thing. So, but at any rate, the next problem is now they got the idea that they're going to string telegraph cable from England to the United States. And that just opened up a giant can of worms. So at that point, it took several tries to get the wire to go across without breaking. There was no math, there was no engineering, nobody knew what was going on, nobody knew what they were dealing with, and it consistently didn't work and failed, and eventually they got it going. And then an archetypal situation in electrical engineering history appeared out of this that basically formed electrical engineering. And at that time, the knowledge of electricity was being heavily advanced by a guy by the name of James Clerk Maxwell, who is basically the center figure in most of your modern, like, relativity and Einstein and electromagnetism. Most of this ties back to Maxwell. Maxwell made a discovery that just kind of twisted everybody's brain inside out. Maxwell was the first person to figure out how to use what's called the Newtonian Leibniz calculus, or what do they call it? They called it, there's a name for it, like elementals or something, where you reduce the points down to zero. What's the infinitesimals? It was the system of infinitesimals, which is kind of like Alice in Wonderland. You have to believe that something continues to exist even though you divided it all the way to zero. But the important thing is it gave the engineers and scientists a way to quantitatively study the condition of change. And it introduced the dimension of time into the study of natural phenomena such as electricity. That was probably one of the most important things that led to the ability of electricity to be engineered rather than just some weird thing that weird machines made that never really did anything other than shock people, and you couldn't do anything with it. It was just toys. It was basically, if you look at the situation in Europe, you have what's called the age of clocks. It was a concept of time was emerging, and where its effect, or how would you say, maybe its conjugate or its relation, really appeared was in the music of the time, which basically comes to a peak with a guy by the name of J.S. Bach. Because basically, when you analyze the structure of the music of J.S. Bach, you see all of your engineering math and situations and the things you're going to deal with in electricity are all basically mathematically fully developed. None of the experiments or the dimensions or any of that stuff, of course, ever went with it. It was pure music. It was a mathematical expression, so to speak. Then after all that kind of got shut down, Bach was basically the Tesla of the music world. When he died, his stuff was destined to go to the junkyard. It just happened to be some guy by the name of Forkel pulled all the stuff out of the scrap heap and got Bach's work, which was all going to the dump, back on the table or in a shelf somewhere so that other people, most notably Albert Schweitzer, could put it all back together again. But that's kind of diverging. So after that point, then the Newton and Leibniz and the mathematicians started to come up with things that change with respect to time, like the gravitational situation. The thing is when something falls through space, it doesn't fall through space at a constant speed. It keeps going faster and faster and faster. But the thing is how does it go faster? What's the rate at which it's going faster? The culture was starting to get the idea of how to express these changes in an abstract dimension, a dimension of time, rather than a dimension of space. So this dimension of time led to what's called Faraday's law, which is how much magnetism is appearing or disappearing with respect to time. I'm going to kind of concentrate on the physics of all this stuff. I'm just right now trying to give everybody an overview of what I'm talking about here, and we're getting through the history up to Tesla. So what Maxwell found is the way the physicists dealt with electricity was the amount of force that it induces on matter. So electricity was measured with scales, just like mass. In other words, if you have so much magnetic force, then it pulls the scale or pushes the scale a certain amount, and that's how you measure electricity. That's how most of your voltmeters and amp meters all worked afterwards when the electrical age was established, was the amount of force delivered against something like a spring. And that was the determination of what type of electrical quantity, what its magnitude was. So Maxwell found a very interesting thing. He found that if you take a certain quantity of the magnetism and a certain quantity of the dielectricity that exists in the space between the magnets and the coils and the whole thing, is it always comes out to be the same numbers. If you multiply them together, it always comes out to be 1 over the velocity of light squared. So Maxwell theorized that this velocity of light must somehow have to do with what he was trying to discover, which was radio. Maxwell wanted to figure out a way to communicate electricity from point A to point B through this primordial ether and the electrical lines of force. So at that time, I'm not quite sure on how they determined the velocity of light, but it would have been through Maxwell that these things were probably discovered. Now, these so-called famous equations like E equals mc squared that we attribute to Einstein and all that are basically all really attributed to Maxwell. These other people just reused the stuff to, make their theories work. But it all basically came from Maxwell. So Maxwell theorized 2 types of electrical propagation through space. One was electromagnetic, and it had to propagate at the velocity of light. And the other one was dielectric. And it became complicated to ascertain what kind of velocity there would be. So Maxwell had to come up with a conjugate to Faraday's law, which could be called the Maxwell law, but it's never expressed this way in the history books. So Maxwell gave enough quantification to the behavior of electrical fields and forces that now people that were physicists who could identify forces and scales and mass and all these type of things had something to work with. And telegraphers were the first ones that were out there that made something that they didn't know how it worked and were hard-pressed to have somebody figure out what in the hell was going on, because the more they would try to develop the system, the more it would resist them. And then when it came to the undersea cable situation, once the thing was all hooked up, they found out that the telegraphic impulses would fall head over heels down the line and come completely scattered out the other end, and the whole thing was a complete disaster. So the physicists came up with an explanation and pounded on it in that direction, which is called the diffusion theory. Now, if I take an iron bar and I take a torch to it on one end, okay, and that end starts to get red hot. If I go down that bar, the bar is getting less and less hot. Okay, and there's a curve to that. It's a diffusion, where the heat is scattered and conducted, and it causes a very characteristic mathematical curve that has to always be the same shape. So the physicists concluded that the electricity propagating down the cable in the form of current and a magnetic field had to propagate in this way, so they attempted to load the signal to deal with that liability the best, which was the wrong direction to go. So some crazy guy by the name of Oliver Heaviside starts engaging in experimental mathematics because the Maxwell stuff was basically impossible to use. I don't think that anybody this day has fully comprehended Maxwell's work, or I don't think anyone's even bothered to read it. It takes years. It's incredible labor. So it's just not happening. So Heaviside took some of that stuff and decided to experiment with it. And Heaviside kind of detested the calculus situation and wanted to come up with a basic algebraic expression that was easily soluble and not all these incredible differential equations and partial derivatives and the things that was just too hard to deal with. You just couldn't apply it to a working situation without twisting your head inside out. So what Heaviside theorized the problem on the cable is the cable is in reality propagating not a magnetic wave, but is propagating an electromagnetic wave. So the electromagnetic wave, having 2 parts, had 2 basic waveforms that had to be kept in match. So Heaviside solved some of the Maxwell's equations to come up with the famous equation in electrical engineering called the telegraph equation. You got it. Okay, the telegraph equation turned 20 pages of Maxwell's work into one simple algebraic expression. I'll write it down here on the board. And that's the first term, the second term. Let's see, let's go to positive one. I'm going to this way and this way. This is called the real part, this is called the imaginary part. That is the archetypal expression of all electromagnetic activity. Everything evolves out of that equation. It's called a wave equation. What it represents is a second order differential. This one is per time squared. This one's scalar. This one's per time, and this one's per time. Everyone that works in electronics recognizes this as the RC time constant. In other words, RC equals T. But there's a lot more to it than that. So what Heaviside found is applying this equation to the situation on the telegraph cable is you had two basic waves. You have the magnetic and you have the dielectric, and then you have the rate at which the wire eats it up, and then you have the rate at which the insulation eats it up. So the problem is the wire eats up the energy faster than the insulation eats it up. So when the magnetic is propagating down the line, it's getting eaten up faster than the dielectric propagating down the line. So what Heaviside did is, being that magnetism was being weakened, Heaviside used iron wire or a magnetic tape in the cable to raise the magnetism to the point where it should have been. Two dissipations were equal, and then all of a sudden all the signals came perfectly clear out of the other end of the line. And this was just simply unacceptable to the Royal Society in London and the people who were running the telegraph business. So they just hounded him right down into the grave. But he wouldn't die so quick, and he wrote a giant 3-volume book on the whole thing and came up with almost every electrical equation and term that we use today. The words Maxwell's equations, which comes out of everybody's mouth, is in every basic book on electrical engineering, are Heaviside's equations. They have nothing to do with Maxwell. He was the one that developed the symbolic math of the curl and the divergence and all that type of stuff. He was the one that basically laid what he said, he got the baggage off of Maxwell. And then electrical engineering from that point on was made possible. Then somebody followed him, because Heaviside didn't like teaching people. And the more complicated he could make it, it seemed like the happier he was. And his books have got little stories about mishaps of people that believe wrong theories and parables, and they're not like your normal engineering book. The guy was what was known as a first-rate oddity. And he was always half ready to eat out of garbage cans. He basically, when he died, part of the reason why he died is because the neighbor kids stoned him with rocks every day, so he couldn't get out of his house. So Heaviside got to meet, like everybody else, the wonderful world of electrical discovery. So if you go through all these inventors, you find out that electrical study really is the tale of Prometheus. You will be rewarded. The eagle will peck your liver until you die. So that's the way it works in the world of electrical discovery. Not a business I recommend anybody get into, unless maybe they've been in the Marine Corps for 16 years. So what happened was another guy showed up by the name of Steinmetz. Now, Steinmetz is where all of a sudden it came into basic, hardcore reality electrical engineering with nothing really half done, or there was no jokes or, any of that. And the reason for this, the reason why Steinmetz didn't get screwed with and got away with everything, as long as it was well hidden in algebraic equations and never said in English. The guy was smart. The books he wrote, the 3 major books he wrote, comes up to about 1,800 pages. Some of the equations are as much as 20 pages long. This guy really got into depth. And the reason why he was allowed to is because of a guy by the name of Nikola Tesla. Okay, there's a whole other class of electrical people, and the most famous one is Edison. Okay, as far as power lines, circuit breakers, fuses, microphones, basic motor generators, batteries, all that type of stuff really was, Edison was the one that pushed it all forward. So Edison's start was a telegraph operator. So Tesla was considered probably the world's best railroad telegraph operator. He could send for days at 30, 40, 50 words a minute and receive and just put everybody underneath the table. And Edison was a kind of an American folk Faraday. In other words, he had no allusions to any higher spirits or higher human causes or, saving the world, any of that type of stuff. Edison just wanted to screw around with stuff and see what he could do. And he started this at a very early age. And what he did is he attached himself to the railroad to the point where they would always give him space on one of the cars or the caboose or something to build his laboratory, until he ended up usually starting a fire from battery electrolyte experiments. So eventually he was grabbed by the ears and flung off the train, and it damaged Edison's hearing from that point on in his whole life, which further endeared him to the telegraph because that was something that he could hear easier than voices or any of those type of things. And a lot of his work was in the area of sound development. He developed the microphone that's used in the telephone today. He developed the phonograph and a number of those sound devices. But Edison decided at an early age, let's see, I got a picture of him there. Where's the main, let's get pictures of these people. The pictures of Edison and the ones that you don't see. You always see these people when they're old and bitter, after they've been screwed from all directions, and they're hissing at the camera. But here's Edison when he invented the light bulb. Whole different guy. So Edison decided that the gas light thing was just too much. The soot, the explosion hazards, all the complications. He was going to figure out a way around it. So it just happened to be at the time that people experimenting with these voltaic batteries had managed to get flames big enough that they were able to produce light. So this gave Edison the inspiration of producing an electric light. And at about the same time, it was found that if you made the voltaic flame with carbon, it would produce a bright light. And so the street lights were already, gas street lights were already doomed, but the arc light was useless for the home because it was high voltage and it still burned and hissed and carried on just like the gas flame did. So Edison came across another experiment in Europe where people were using platinum wires heated to orange heat inside vacuum bulbs, and they were starting to get an electric light. But if you got it to any usable light, it just kept melting. So Edison and his crew experimented and experimented and experimented and experimented with everything they could find on the face of the earth. They tried every metal, every combination, everything, and it was always the same deal. Once you got that thing up to white light, if it lasted for 5 minutes, you were lucky, and it went dead. So Edison, ready to give up, just about sick and dead from the whole ordeal, somehow got a hold of a bamboo fan and was looking at the fibers and playing with them and got the idea that if he cooked one of those fibers to the point where it turned to carbon, and the fibers were so strong that it still sprang like metal, that the carbon, which naturally wants to go white hot, would just make a natural inside filament for the light bulb. And sure enough, it worked. Gas companies didn't like that. Okay, so needless to say, the gas companies were not his friend. So Edison, trying to get the city of New York to adopt electric lighting system, of course, immediately comes up against the gas companies. And they have every trick in the book to try to put them out. So what the gas companies do is, okay, New York wants electric lighting system. What the gas companies did is they petitioned the city to force Edison to put all the electrical underground, which absolutely no technology existed for, because the only electrical technology was the telegraph wire. In Edison's situation, instead of being a little 8-gauge iron wire, it had to be a 2-gauge piece of copper cable. So how was he going to make all this go underground? So Edison didn't give up. So what he did is he took pieces of copper pipe and soldered them all together, wrapped them in rope, poured tar into cast iron pipes like sewer pipes, into what are called Edison tubes. They actually used to be, when they dug up downtown San Francisco to build the financial district, all the old Edison tubes came up out of the ground. And that's what they were. They were iron pipes filled with tar with a copper pipe in the middle. So Tesla set up this network of electrical plumbing under all the streets of New York City. Okay, got enough subscribers for the lights, put the whole thing in, built the steam-powered generating plant. None of this had ever been done before. He was completely on his own. The guy did not know a bit of any of the physics at the time. There was no volt, there was no amp, there was no ohm, there was no Henry, there was no farad, there was none of these things. That's what these people were up against. You couldn't open up the electrical engineer handbook and get your resistance tables off the wire. I mean, these guys had to make it out of zero, nothing. So at any rate, they got the thing all together. It was the first power station in New York City. It was called the Pearl Street Station. Okay, and they closed the switch and they tried to hook all the generators in parallel and it blasted. So they got it going in about several hours. They got the whole thing lit, and then hence that point, history. So now the next thing is not only the light bulbs, but now they had the idea of these telegraph relays. Now they got these things spinning in the form of motors. Edison started developing giant telegraph magnets into motors. The famous Edison motor is 2 very long solenoidal coils that stand almost 8 feet high, and then there's a rotor down in the bottom. You have these large electromagnetics, and what Edison had done was basically just amp up the telegraph magnet, because that's all there was to work with at the time. So this is where Nikola Tesla comes in. So Nikola Tesla comes to the United States. Okay, he's almost turned back because he doesn't have any money. But he has one thing that gets him in. He has a letter of recommendation from the Edison Electric Company in France, if I remember right, either France or Hungary. And Edison lets the guy in. So Tesla goes off on his rotating magnetic field discoveries and all of these things, and Edison just looks at him and, is not interested in any of this stuff. What Edison wants is Tesla to work on motors. So Tesla, because he's already starting to gain a conceptual knowledge of how this rotating electrical thing's supposed to work, points out to Edison that these big telegraph coils are foolish, that the coils are supposed to be wrapped inside the motor. And Edison said, if you can develop that, I will give you $25,000. So needless to say, Tesla went right to work on it. And in a short time, he had developed the present-day direct current motor, which is basically a square block instead of a tall column, and it later became rounded off. So it turned out to be a great success, and Tesla didn't get a dime of his money. So Tesla left and was digging ditches on the street until some Western Union people came by and wanted to know if he would work with them on some of their projects, and he worked his way up, and he worked his way up. And Tesla decided what he was going to develop. He was going to come up with a motor that didn't need all the sparking and rigging and all the real fine wire on the coils and all these complications. He was going to eliminate that up and come up with the perfect magnetic whirlwind, where the rotor would spin in the ether with no contact on it whatsoever by setting up a magnetic vortex. But there was no way to conceive such a thing at the time, because basically everything in electricity was a positive, negative reality, so you couldn't make anything spin, because it could either just go back or forth. And they fought, and they fought, and they fought, and there's no way. You had to have the commutator has the carrot in front of the horse to trick the field. What a commutator does in the motor is the windings come around, there's a switch. And what it does, because the windings only can turn so far before we've been wanting to be pushed back in the field again or get stuck, the commutator switches in the next set of coils as the rotor turns around. So it creates this kind of phantom thing where the coils are always trying to go towards something, but then they get disconnected in the previous batch. So it's like a lineup around the thing. And fools the motor in the spinning, but this thing throws off all this dust and sparks, and it's problematic in maintenance, and the motors are horribly inefficient because they have to have these big magnet coils with lots of current flowing through them. So Tesla fought the problem in his head, and everybody told him it was impossible, and he was an idiot for even trying. Think about it. So Tesla was reciting some poetry one day, and then watching the sun go down, and then had this idea, because of the poem he was reciting, was talking in such a fashion that if the sun's going down here, it's got to be coming up somewhere else, and got the idea of the quadrupolar polarity, where you have two plus and minuses at right angles to each other, and you switch them. So what Tesla developed was a way to make alternating current carry around, just like the phases of the moon. And drew the whole thing out in sand. The thing appeared in a flash in his mind, and everything was invented at that point. Because Tesla could go into visions so intense that Tesla was renowned for building motors in his head and running them for months to see the rate of bearing wear. So you're not a normal individual. So we can only imagine what went on in his head. So Tesla worked with this and got it developed, but gee, nobody seemed to want it. And Edison got really upset about the whole thing. So Tesla's about ready to give up on it. He meets a guy by the name of George Westinghouse. George Westinghouse made parts for railroad trains, mostly the brake system, the Westinghouse Brake Company. Okay, now some of those brakes are magnetic. So he was already geared up for coils and solenoids and things to actuate the brake mechanisms. So Westinghouse decided he had enough money, he was going to support Tesla, and they were going to make this thing and make it work. Well, Edison didn't like this at all, so Edison turned into the gas companies. The very thing that screwed Edison. Edison repeated the whole process and delivered it all to Tesla. So what Edison did is Edison started getting reject circus animals, hiring kids to gather up dogs and cats off the street, and he would have them Westinghoused on stage, which was about 2,000 or 3,000 volts of alternating current, about several amperes. So he had to have a big machine somewhere to produce this, but that never really showed up in any of the old pictures. But what did show up in pictures was elephants just crumbling to the ground with smoke shooting out of them. So we're talking about 50, 75 kilowatts to do that.
Ouch.
The electric chair is 5 kilowatts. So you cook up a big slab of meat in the oven, you usually got to have about a 5 kilowatt cooker going for a couple hours. So that gives you an idea how much juice it is they put through the body. So Edison invented the electric chair using alternating current in order to put Tesla out of business, and then started spreading these stories of the fantastic dangers of alternating current. So Tesla was getting rocks through the window and the whole deal, and he's trying to push all this forward. But Tesla really pulled a good one on him. Okay? At this point, Tesla had already invented all that motor stuff, and he was on to something even bigger, even more fantastic. So he wasn't really worried about a lot of things other than just getting his money. So here's what Tesla discovered. Tesla discovered a completely new type of electricity, unlike DC or AC. Another type of electricity. It's called impulse electricity.
You need to stop for just.
This impulse electricity behaved in a fashion that was completely extraordinary. It was getting back into the ether electrical concepts, because what it would produce would be so bizarre that it almost looked like the aurora borealis appearing around his coils. So what Tesla found is this type of electricity, rather than being damaging to the body actually seems to benefit from it. So Tesla was destined to give a demonstration of his more recent researches. He was already famous for his motor, Okay, and Steinmetz was already put in business in order to mathematically analyze the Tesla system so that General Electric could defeat Westinghouse in the Tesla patents. So that's how Steinmetz got basically started in the thing, and Tesla built all this stuff in his head, and he left no engineering math. He didn't need any of that. So there's no way that other people could duplicate his devices, because there was no engineering. You didn't know how much iron to use. You didn't know how much copper to use. People would try to use these motors, and for some mysterious reason, they would just keep burning up. And it was Steinmetz was the one that discovered why. And that made him famous and put him in his lifelong position as the founder and director of General Electric Research Laboratories. So Tesla devised his vacuum tubes and his transformers and all the things that technology that he developed with this impulse electricity, and gave a presentation in Europe. And it was so fantastic that Tesla was immediately a worldwide hit, not only as an electrical scientist, but as a magician. What Tesla had accomplished, which nobody's been able to duplicate to this day, is he connected himself to these devices that he packed over there, closed the switch, and how many people know what a neon bulb is? You know that the funny glow that covers the metal electrode? It's like a fire, but it's not really a fire, and it kind of looks like a jelly, but it's not really a jelly, but it's the plasma, the glowing plasma in the neon bulb. Tesla's whole body lit up like a neon tube cathode, on stage, without a burn or a mark on his clothes. And then he pronounced, "Here are the dangers of alternating current," and laughed. So that ended the whole DC-AC controversy right then and there. Plus, J.P. Morgan needed to make money off of it. So nothing could stop it at that point. So it went. And Tesla kept pursuing this technology. So what Tesla found is Tesla came up with a situation that kind of defeated the whole physics end of the electrical engineering world, and that's basically why there's no knowledge or information on it, because it's just completely blocked off. These things are impossible. They can't happen. But, you build Tesla's devices as he prescribes in his writings, and you will get all of these effects. I've duplicated just about every Tesla experiment. In fact, actually, I'm very famous for being probably the only person that has ever duplicated Teslas in experiments. And it's not because I'm smart or that I talk to space aliens. What it is I don't make any improvements on the historic study. It's that simple. I just do exactly as instructed, and it all works exactly as described. So Tesla had come up with a way, with this high-frequency experimenting and the mechanical analogs that he developed to go along with it, to defeat the action-reaction law, or the Newtonian law, where every force has a counterforce. Tesla came up with a way to produce a push without having to lean against anything. He did it both electrically and mechanically. So what Tesla found is that similar devices that operated on the same frequencies or rates would communicate energy between each other. So what Tesla did was basically, at that time, discover radio. But the thing about Tesla's radio that's different is there's no real energy loss between the two devices. In other words, you can transmit from one device to the other, and there's not, it's like there's nothing going on in between. It goes right to the receiving device. The electrical meter doesn't start spinning at the transmitting station until the space heater is plugged in at the receiving station, and there doesn't seem to be anything measurable going on in between. And Tesla's aim was to produce a worldwide power system that was based on this principle, and the power system would be tuned to the natural resonant frequency of the Earth, and you could just simply disconnect all the generating stations, because the solar system would run the electrical plant. It would be one with the electrical system of the Earth. So what Tesla had to do is he had to do an experiment in Colorado to prove if he could resonate the Earth and make it take off. And it's too bad in that day and age there weren't videotape cameras, so somebody could have got documentation of what this guy must have unleashed. So what Tesla did is he had figured out the frequency of the Earth, or the harmonic that he could use, which he started working at about 80 kilocycles, and eventually he worked his way down pretty close to 50 before the thing was all tuned up. It was a transformer that had a coil 50 feet in diameter. The output terminal of the thing was on 100 and something foot, at least 100 and something foot mast. And the idea was Tesla was going to send an electrical pulse into the Earth. It would bounce off the inside of the Earth and come back at a certain time with a certain increase or decrease in energy level. And he was going to continue this process, in microsecond groups as these 50 kilocycle waves are echoing in the planet, until what he would produce, it would be a giant electrical fountain of the Earth's activity at that point in Colorado, which kind of is a place where it was safe to blast because nobody would get hurt. The elevation was good, and this is the place he chose to do it. So when Tesla closed the switch, after all the experiments and tests, he produced for a period of about maybe 1 minute a standing lightning bolt at the terminal of his giant transformer in the building that contained it. Not just one pop, almost standing lightning bolt, modulated at about 5,000 cycles a second from his capacitor discharge switch. So the sound must have been something that was unfathomable to describe. Tesla succeeded in concentrating the entire electrical activity of the Earth into his station in Colorado. So he packed up his bags and moved back to New York, and Long Island began to build the final station where this was not an experiment. It was something that worked. So he could start applying it to electrical transmission.